Hey everyone. So today's lesson is some more with the special segments we've been learning about, but it's kind of a continuation of it. So there's a few vocab words we're going to learn. The first one is concurrent lines. Concurrent lines are three or more lines that intersect at a common point. That point is called a point of concurrency, and that's what we're focusing on today, points of concurrency. And so that's the point where the concurrent lines intersect. Now, last week we learned the four different special segments. There's medians, altitudes, perpendicular bisectors, and angle bisectors. When you have a triangle with three medians, three altitudes, three angle bisectors, three perpendicular bisectors intersecting, they make a point of concurrency. So each special segment has a point of concurrency. So the first one is a circumcenter. The circumcenter is the point where the three perpendicular bisectors intersect. So as you can see this picture here, this is a circumcenter because each of these 1, 2, 3 lines, those are all perpendicular bisectors. Okay, circumcenter theorem says that when the perpendicular bisectors intersect at a point called the circumcenter, it is equidistant. That just means the same distance from the vertices of the triangle. So if you look at this picture here, let me zoom in a little bit more. If I told you that G is a circumcenter, you could conclude that these three segments are congruent because the theorem that we just learned says that the circumcenter is equidistant to the vertices. So that makes these three segments the same. Not only can you tell that those three are the same, but because it's a circumcenter, that means that each of these segments is a perpendicular bisector. So that would make these two equal. This is a perpendicular bisector, so that would make these two equal. And then this is a perpendicular bisector, so that would make these two equal. So you have lots of congruent segments when you have a circumcenter. In this example right here, I'm just going to list the ones that were congruent because of the theorem, which is BG being congruent to AG and CG. So that represents the distance from the circumcenter to the vertex. Okay, so that's a circumcenter. The next one is called an incenter. And so you can tell from this picture right here that the incenter is the point where the three angle bisectors intersect. And so if you look at this picture here, I can tell that is the angle bisectors because see how we marked these two angles the same, these two the same, and then these two the same. So this would be an incenter. So there is an incenter theorem. The incenter theorem says that the incenter is equidistant from the sides of the triangle. So it's not just equidistant. It's not like the other one where it was equidistant to the vertices. This one's equidistant to the sides. So if we take a look at this picture here, if I gave you that D is the incenter, right here, here are the sides of the triangle. So the segments that go from the incenter to the sides, those are all going to be congruent, those three. So we'd have ED is congruent to FD is congruent to GD. Now, one thing about those segments that are congruent is the distance between a point and a side is the shortest distance, which is also perpendicular. So when these little segments are drawn in, when you have an incenter, they're always right angles. Most of the problems that you're going to do, they mark the right angles for you, but just in case, they're right angles. Okay, so that is an incenter theorem. The next one is a centroid. centroid, if you look at this picture here, centroid is where the medians intersect. See how on this side, these two are equal, these two are equal, and then these two are equal? That means that these three segments are medians. So a centroid is the point where the three medians intersect. And there is a centroid theorem. Centroid theorem is a little bit different and it sounds confusing to start, but it actually is pretty easy once you practice it. So centroid theorem says that the centroid is 2/3, of the distance from each vertex to the midpoint of the opposite side. So 2/3 of the distance from each vertex to the midpoint of the opposite side. And so let's take a look at the picture. Let me explain that a little bit better. If I told you V is a centroid, let's take a look at this median here, QU. V, the centroid, is 2/3 of the distance from Q, the vertex, to U, the midpoint. So this piece is 2/3 of the whole thing. This piece is 1/3 of the whole thing. So basically how this theorem works is we give you certain numbers, certain measures, and then we ask you to find the missing ones. And so if you think about it, if this is 1/3 of the whole thing and QV is 2/3 of the whole thing, think about the relationship between 1/3 and 2/3. 1/3 is half of 2/3, right? 1/3 plus 1/3 would equal 2/3. So when you're doing these, I'm going to make a little bit note over here actually. When you're doing these, there's each median is always broken up into a longer piece and a shorter piece. The shorter piece is half of the longer piece. So the short piece, let's add this little note in here, of the median is half of the long piece and 1/3 of the entire median. So that should help. I'll kind of show you the easy way to solve these problems. So let's first start with this first example. It says QV is 4. So QV is here, so that's 4. So when you're given a segment, you want to ask yourself, is that the long piece of the median or is it the short piece? Or is it the whole thing? Sometimes they give you the whole thing. This one is the longer piece. The piece that's closest to the vertex is the 2/3 piece. That's the longer one. Then the piece that's closest to the side, which in this case VU, that one's the shorter piece. So the longer piece is always double the shorter piece. So that means that if this one is 4, VU is just half of that. It's 2 because it's 1/3 and this is 2/3. So it's half of it. So to fill this in, VU is 2. And then what's the whole thing? Well, we can just add 4 plus 2, which is 6. Okay, so that's the first type, is when you're given the long piece of the median. This next one, PT is 9. PT is the entire median is 9. I'm not going to label that because it's hard to label it when it means the whole thing and there's all this going on. So when you are given the entire median, it's quickest and easiest to find the short piece of the median first. And so the short piece is 1/3 of the whole thing. So we really just want 1/3 of 9. Basically 9 divided by 3. So 1/3 of 9, or 9 divided by 3, is just 3. So this piece VT is going to be 3. Once I get VT, I can easily get PV by either doing 9 minus 3, which is 6, or when you have the short piece and you want the long piece, you just double it. So 3 times 2 is 6. And so that's VT and PV. So if you're given the whole thing, divide it into 3, divide it by 3 to get the short piece, double it to find the longer piece. Okay, so now the last one I gave you is SV is 2.5. So let's go back up here. SV is 2.5. So SV is 2.5. That's this little piece here. So that's the short piece of the median. So let's find the longer piece of the median. To get that, we're going to double it because the long piece is twice the short piece. So 2.5 times 2 is 5. So VR is 5. And then SR, the whole thing, you're just going to add 2.5 and 5, which is 7.5. So that's how you do centroid problems. Again, it looks intimidating, hearing 2/3, 1/3, whatever, but it actually is pretty easy. Okay, the next thing we're going to do is the centroid formula. So sometimes we give you ordered pairs that make a triangle, and we ask you to find the coordinates of the centroid. This is the centroid formula. It's sort of like the midpoint formula, except there's 3 points. So you're going to add the x's, divide by 3, add the y's, divide by 3. So here are my x1, x2, x3. So I'm going to add those. 3 plus 2 plus 3 over 3. And then my y's, 1, 2, 3. So 1 plus 2 plus 5 over 3. And then just reduce. So 3 plus 2 is 5, plus 3 is 8. So we're going to have 8/3, comma, 1 plus 2 is 3, plus 5 is also 8. So 8/3. And you can just leave it like this. You don't have to make them decimals if you don't want to. I usually just leave it in fraction form, and that's totally fine. If it was something that could be reduced, you would want to reduce it. Like if I got 12 over 3, you'd just write 4. Okay, the last thing I'm going to define, but we're not really going to use it to be honest, but just so you know that it does exist, is an orthocenter. It's also just got cut off rather. An orthocenter is the point where the 3 altitudes intersect. So it's the point where the 3 altitudes intersect. And the reason why we're not really going to do anything with this is because there's no theorem or anything with an orthocenter. There's not really anything that's true about the segments or anything like that. So that's why we don't really do anything with it. There is like a long algebra problem we could do with the orthocenter, but we're not going to do that this year. So that's it. Those are the points of concurrency. We have circumcenter is where the perpendicular bisectors intersect and it's equidistant to the vertices. We have an incenter. That's where the angle bisectors intersect and it's equidistant to the sides. We have a centroid. That's where the medians intersect and it's 2/3 of the distance from the vertex to the midpoint. And then we have an orthocenter, which is where the altitudes intersect. And there's nothing really to say about an orthocenter, just what it is. And so that's it. We will do more of this tomorrow, and let me know if you have questions. All right, have a great day.